On this last example, we're using what's called the method of Frobenius to find two linearly independent solutions about x equals 0. Want to form the general solution to 4x times the second derivative of y plus 2 times the derivative of y plus y equals 0. With the method of Frobenius, you might not have solutions in the form of a polynomial function, but they'll be similar to that form. Here, notice that the difference is that we have x to the n plus r instead of x to the n. So this will have a polynomial function multiplied by some other power of x, which may or may not be a polynomial. There's my pen. So you could have this y actually could also be written in this form. Could be y is equal to x to the r times the sum as n goes from 0 to infinity, cn x to the n, where this r could be any power, including a possibility of a fractional exponent, like 1/4. And so if you do have something like 1/4, then your solutions are going to look like x or c0 times x to the 1/4 plus c1 x to the 5/4 plus c2 x to the 9/4 and so forth. Notice this is just x to the 0, and then you multiply by an extra x to the 1/4. And this is x to the first plus 1/4 power to give you 5/4. So, but otherwise we work this pretty much the same way that we did before, but we need to take into account the values that r can be. We can find those values for r by substituting into this differential equation and then solving for r. So when we substitute in, first we want to find the expression that's equivalent to y prime and y double prime. You can find y prime by bringing down this exponent, m plus 4, and then m plus r, and then decreasing the exponent by 1, m plus r minus 1. And for the second derivative, you'd bring down the m plus r minus 1, and decreasing the exponent by 1 will give you an m plus r minus 2. Substitute those into the differential equation. Notice I have 4x times, this is my second derivative term, plus 2 times my first derivative term, plus y. And we want to do the same thing that we did in the previous case. If we have any x's outside of the summations, we want to bring those x's inside. In this case, I have x to the first outside, so bringing that inside will add 1 to my power of x. It'll make this m plus r minus 1. And the 4 can also be brought inside. This 2 can be brought inside. That's what I did here. And then you want to make a substitution so that these powers of x's are all the same. Now notice they all involve n and r. And you want to let k equal, in this case, in this last term, k is equal to n. Here, just ignore the r and here you get k is n minus 1, so that each exponent is n plus r. And here k is n minus 1. So if k is n minus 1, then n is going to be k plus 1. So in this first case, when n is 0, you start with k equals negative 1. N is k plus 1, k plus 1 plus r. This will be k plus 1 plus r minus 1, and the minus 1 and the plus 1 will cancel to give you k plus r, x to the k plus r. Here 2c k plus 1, you get k plus 1 plus r, x to the k plus r, and here you're just replacing the n's with k. Okay, so after you get all the same powers of x, x to the k plus r, then you want to look at your lower index, and you want to make sure that each of these is expanded so they start at the same location. You want to start at the higher number, at 0. And so for these first two summations, you want to expand, letting k equal negative 1, and then write the remainder of the terms starting at 0 to infinity. Okay, here I have the previous equation, and now I want to take out these first terms. So we'll start by letting k equal negative 1. There we go. K equals negative 1. And when k is equal to negative 1, this becomes C0. This negative 1 and 1 cancel out to give me an R. This becomes negative 1 plus R, or R minus 1. This becomes negative 1 plus R, or R minus 1. And then I can start my lower limit at 0, so that my summation goes from 0 to infinity. Here I just copied down the terms. And here again I want to expand. I want to let k equal negative 1, so this becomes 2c0. The negative 1 and the 1 cancel to leave me with r, and negative 1 plus r gives me an r minus 1 here. And then I can write the remaining terms in my summation as going from k equals 0 to infinity. My last summation just carries along. So notice in this case these do not cancel out to give you 0 because you don't have any zeros as a factor. But you want to take those two terms. They are like terms. X to the r minus 1 is the exponent in both cases. You want to take both of these terms and combine them. Okay, so we're going to combine these terms. Notice that x to the r minus 1 is factored out to leave me with well, let's see what we get when we simplify. And I also have a C0 and an R factored out, and a 2 factored out. So if I factor out 2, that's still going to leave me with a 2. I have an R and a C0 factored out. So 2, C0's factored, R's factored. I'm left with an R minus 1. And here I have 2 C0R, x to the r minus 1. This is all factored out. So I have 2 C0R times 1 and then the x to the r minus 1 is my term. So this part is what's factored out. And you get the 2r minus 1 by distributing through by the 2r here to get 2r minus 2. And then from here you have plus 1. Plus 1. And that minus 2 plus 1 gives you this minus 1. Now on my summations, because I have the same limits at the bottom and the top, I can also factor. I can combine these. I'm factoring out the x to the k plus r. That's my x to the k plus r. And here I have a k plus 1 term and another k plus 1 term. So these are like terms. And then I have my k term. This is my k term. That's this one up here. And then for my c k plus 1, let's see, here everything is multiplied by 4. So I've got 4 k plus 1 plus r times k plus r plus 2 k plus 1 plus r. Notice I have a 2 in common. That's this 2 that's factored out. So if I factor out the 2, that's still going to leave me with a 2 here. Factor that out. I have a k plus 1 plus r in common. And that's this k plus 1 plus r factor. And that leaves me with just a 1 here. And here I have a 2, so I get oh yeah, I have 2k plus 2r plus 1. And that's this, 2k plus 2r plus 1. So everything else is my common factor. This is all a common factor along with the x to the k plus r power. Okay, now just like before, we set the coefficients equal to 0 and solved to get our general solution. Here, because I have terms outside of the summation, I know that this coefficient has to be equal to 0, and that's where I get this equation. 2 times 2r minus 1 times r times c0, and then this is just my x term. I want to set this part equal to 0. I don't need the c0 part or the x to the r, but set this equal to 0 and solve for r, and we get 2 equals 0, which is not true. We get 2r minus 1 equals 0, which is going to give us r equals 1/2, and we get r is equal to 0. Gives us this one. So this tells me there are 2 values for r that will work, 1/2 and then 0. And I can get my recurrence relation by looking at the coefficients of all my other terms. There it is. Okay, so if I take this coefficient of x to the k plus r and set it equal to 0, I can solve for ck plus 1 by bringing the ck to the right side of the equation, and then by dividing by all of this. This all comes down to the denominator. And here's my recurrence relation in terms of K and R. Okay, so we're going to take this recurrence relation and we're going to take the fact that R can be 1/2 or R can be 0 to come up with our linearly independent solutions. Let's start by looking at R is equal to 0. That's probably the easier one. When R equals 0, the recurrence relation, these R's just drop out. The recurrence relation becomes negative ck over 2k plus 1 times 2k plus 1. And I can get the coefficients by letting k equal 0 to substitute 0 in for k. You get negative c0 over 2. Let k equal 1. Substitute 1 in for k. Eventually you get c0 over 24. Let k equal 2, so that eventually, simplifying and plugging values in, you get negative c0 over 720. K equals 3. You end up with c0 over 40,320. And k equals 4. You end up with negative c0 over 3,628,800. Now you can put these values together to come up with a general solution. Our general solution is going to be x to the 0 power. That's from this R equals 0 right here. R equals 0. That becomes your exponent on your x, and then multiplied by the polynomial. You've got c0 minus c1 is negative c0 over 2, x plus c2 is c0 over 24. That's the coefficient of x squared, and so forth. And that continues on and on and on. To find our second linearly independent solution, we want to choose the other value for R. We want to look at what happens when R is 1/2. And when R is 1/2, we get inside this parenthesis, we're going to get k plus 1 plus 1/2. 1 plus 1/2 is the same as 2 halves plus 1/2. Gives you 3 halves. And then when R is 1/2, 2 times 1/2 gives you 1. So you get 1 plus 1 is 2. Because I didn't want to work with fractions, I multiplied through by this 2. So I got 2k plus 3, and then I have 2k plus 2. And again, you want to substitute values into this recurrence relation and simplify as much as possible. So I get the coefficient for C1 should be negative C0 over 6. The coefficient for C2 should be C0 over 120, and so forth. And here are my first 5 coefficients. The C0 is also C0, so we actually have 6 coefficients for the 0 through 5th term. And we get our second linearly independent solution. This 1/2 is from our value of R. R is 1/2. And that gets multiplied by this polynomial expansion. And notice that each one of these, the coefficients come from our table. Negative 1/6, 1 over 120, negative 1 over 5040, and so forth. This is our second linearly independent solution, and to get the general solution, we want to put those 2 solutions together. This C0 is an arbitrary constant that you multiply by, And because I didn't want to use C0 again, I let my constants be K1 and then K2. You just want to use a different constant for each solution. And I also multiplied out. In the first case, you didn't need to multiply anything because x to the 0 is 1. But here, you needed to multiply out by x to the 1/2. Or just add a half to each exponent.